There are places on Earth where volcanic arcs still burn. Along the edges of the Pacific, chains of volcanoes rise where oceanic plates are forced beneath continents, where magma is continuously generated deep below the surface and delivered upward through fractures in the crust. These arcs are loud, violent, and obvious. They announce themselves with eruptions, earthquakes, and steaming mountains. But there is another way to find a volcanic arc, not by looking for volcanoes, but by looking for what remains after the volcanoes are gone. A volcanic arc begins far from the volcanoes themselves, at a boundary between tectonic plates. When a dense oceanic plate sinks beneath another plate, it is carried downward into hotter and higher pressure conditions. As it descends, minerals within the slab break down and release water and other volatile rich fluids into the mantle above. Those fluids do not melt rock on their own. Instead, they lower the melting temperature of the mantle, allowing portions of it to partially melt. That melt becomes magma. Over time, it rises through the crust, pooling in magma chambers, feeding dikes and sills, and eventually erupting at the surface as chains of volcanoes align parallel to the subduction zone. This is how volcanic arcs are born. In the modern world, these systems are easy to recognize: the Andes, Japan, Indonesia. They are marked by steep volcanoes, fresh lava, and constant tectonic unrest. But Earth does not preserve most of its arcs in this pristine state. Given enough time, erosion strips them away. Mountains collapse, volcanoes are worn down grain by grain. What once stood kilometers above sea level is ground flat, and eventually, the surface cuts downward into the crust itself. When that happens, the arc doesn't just disappear, it is revealed from below. Northern Australia is one of the few places on the planet where this has happened on a continental scale. In the Northern Territory, within the ancient North Australian Craton, the land has been stable for so long that erosion has peeled away entire mountain belts. What remains is not the surface expression of tectonics, but the machinery beneath it. Here, in the Pine Creek Orogen and its surrounding domains, we are standing inside the roots of a Paleoproterozoic volcanic arc system that was active nearly 1.9 billion years ago. At that time, this part of Australia did not resemble the flat, quiet landscape seen today. The crust was thinner, hotter, and tectonically active. Oceanic lithosphere was being consumed along a convergent margin, driving magma generation deep below what is now the top end. The volcanic front itself has been erased, but its foundations remain. Deep within the crust, large volumes of magma crystallize slowly to form I-type granitoids, rocks that record their origin in a subduction-modified mantle. These intrusions, now exposed at the surface in the Nimbuwah Domain, represent the frozen magma chambers that once fed volcanoes overhead. Surrounding these intrusions are thick packages of metamorphosed sedimentary and volcanic rocks. They began as ashfalls, volcanic debris, marine sediments, and chemically active shales deposited in basins adjacent to the arc. As tectonic convergence intensified, these rocks were buried, folded, and heated, reaching green schist and amphibolite facies conditions. Thrust faults stacked the crust. Isoclinal folds tightened the stratigraphy. The entire system was thickened and driven downward as the arc matured. To the west, the geological story shifts subtly. Instead of deep burial and compression, the rocks record high temperatures at relatively low pressures, accompanied by arc-related mafic magmatism. This is the signature of a back arc environment, a region stretched and heated behind the main volcanic front. Together, these domains form a complete subduction system, preserved in cross-section, arc route to the east, sedimentary and structural traps in the centre, and back arc extension to the west. What makes this arc incredible is not just its age, but its level of exposure. In most parts of the world, these rocks remain buried kilometres below the surface. In northern Australia, erosion has removed that overburden entirely. The volcanic edifices are long gone, the lava flows are gone, the ash layers are largely reworked or metamorphosed. What remains is the plumbing, the intrusions, the altered wall rocks, and the pathways once used by fluids moving through the crust. Those pathways are the key to understanding why this region is so richly endowed with gold and uranium. Volcanic arcs are not just magma factories, they are fluid engines. As magmas cool and crystallize, they release hot, metal-bearing fluids. At the same time, tectonic compression fractures the crust, creating conduits that allow fluids to circulate over vast distances. When those fluids encounter the right chemical and structural conditions, metals are deposited. In the Pine Creek region, gold is closely associated with late to post-orogenic granites intruded into folded sedimentary sequences. The rocks were already prepared. Carbonaceous shales, iron-rich layers, and reactive lithologies lay folded into anticlines and cut by shear zones. When gold-bearing fluids migrated through these structures, chemical reactions caused gold to precipitate, often locked within arsenopyrite or concentrated along quartz veins. The result is a gold system that appears structurally controlled at the surface, but is fundamentally rooted in arc magmatism at depth. Uranium followed a different but related path. Unlike gold, uranium is highly mobile in oxidized fluids and highly sensitive to changes in redox conditions. In the Pine Creek Orogen, uranium deposits are concentrated near the unconformity between ancient crystalline basement and overlying sedimentary rocks. Oxidized fluids derived from younger basin sandstones migrated downward along faults and fractures, eventually encountering reduced rocks rich in carbon and sulfides. At that boundary, uranium was reduced and precipitated, forming some of the world's most significant unconformity-related uranium deposits. Crucially, the architecture that made this possible was inherited from the arc itself. The same structures that once fed magma upward later became fluid pathways. The same deep-seated faults that accommodated subduction-related deformation were reactivated during later basin evolution. The arc did not just create metals, it built the framework that allowed those metals to be concentrated long after volcanism had ceased. Today, none of this is obvious at first glance. The Northern Territory does not look like a former convergent margin. There are no volcanoes, no trenches, no smoking peaks. But beneath the soil and vegetation lies a geological cross-section that would normally require kilometres of drilling to see. Australia's ancient stability has done something rare. It has stripped away the surface and left the internal anatomy exposed. What appears to be a quiet craton is, in reality, the dissected core of a long-vanished volcanic arc, a place where magma once pooled deep underground, where fluids once surged through fractured rock, and where conditions for gold and uranium enrichment were quietly assembled. The volcanoes are gone, but the evidence of how they worked and what they left behind is still written into the rocks of the Northern Territory. What makes this exposure so unusual is its scale. This is not a single dissected volcano or a small eroded arc fragment, but a region tens of thousands of square kilometres wide where different levels of the same system sit side by side. In one place, you are standing in metamorphosed marine sediments that once lay on the arc's flanks. In another, you are walking across granite that crystallized kilometres below the surface, never meant to be seen. Fold belts, shear zones, intrusive contacts, and basin unconformities are not isolated features here. They are parts of a single tectonic machine, preserved in pieces and laid bare by time. It is a rare opportunity to read a convergent margin not from its surface expression, but from its internal anatomy. That perspective changes how the Northern Territory is understood. Rather than a passive, featureless interior, it becomes the exposed core of a system that once shaped an entire continental edge. The goldfields and uranium provinces are not geological accidents. They are the predictable outcomes of arc construction, deformation, burial, and fluid flow operating over immense spans of time. Australia did not lose its volcanic arcs, it outlived them, and in doing so, it has preserved something far rarer than volcanoes themselves. A direct view into the deep processes that built continents and concentrated the metals that modern societies still depend on. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.